So in this lecture, following the graph theory basics, we will look at one other standard problem known as the MaxFlow problem. So previously, if you recall, we have seen what is a graph and what are the different types of graphs, and how to traverse a graph using depth first search and breadth first search, and how to find a minimum spanning tree in a graph. And in the recent lecture, we have seen how to find the shortest path in the graph. Okay. So today we will look at another standard problem called the MaxFlow problem. So if you have seen the previous lecture, so you have pretty much have the basics already ready with you. So all you need to know is what is a graph and what is this type of graph. So what we are looking at in this lecture is directed and weighted graphs. Okay. So we have graphs and each edge is also having a sense of direction and also some weight associated with it. Okay. So we'll also refer such graphs which are directed and weighted as networks. Okay. So when we use the term network, it is nothing but a graph with directed edges. Okay. And we also have weights associated with each edge. So, and you already know what is a depth first search and how to do a breadth first search. So let's move on to the MaxFlow. So before we move on to know what the problem is actually, so let's look at some basic terms which are associated with any network flows. Okay. So think of the problem this way. So you are given some network of water pipes and junctions. Okay. So these are all the junctions, the vertices we have shown, and the water pipes are represented using the edges. So there is a water pipe from C to T, and we have a weight 2 associated with that edge. So instead of calling it as a weight in here, so we will in turn call this as capacity. Okay. So what does this edge represent? So with respect to a flow problem, so this represents an edge from C to T and weight 2. So if you look at in terms of the water problem, so this also means we can send 2 units of water from C to T. Okay. So we can send water from C to T, and how much can we send? So we can send at most 2 units of water. So the next term is the flow. So even though we can send maximum 2 units of water, so we can actually send either 0 or 1 or 2 units. Okay. So in the final solution, so what is the amount of water that actually goes through this edge is called the flow. So we in turn say that 1 unit of water is flowing from C to T. So the problem constraints say that the amount of flow that is going through any edge should be less than or equal to the capacity of it. And of course we will look at the only integer flows in this session. So the next term we will look at is what is meant by to augment something. Okay. So if you have a solution, if you can improve that solution or increase the flow, that is called as augment. Okay. So this is a direct dictionary definition of what is meant by augment. So just to increase and make the solution better. So what is a MaxFlow problem actually? So given a network of water pipes, and some of the pipes are fat and some are slim. So we refer the fat pipes as the ones with more capacity and the slim ones are the ones with less capacity. So what is the maximum amount of water that can flow from S to T? Okay. So these are the notations we will follow. So we will refer to the source vertex as S, and we will refer to the sink as T. So if you look at the previous graph, so this is the source and this is the sink. So and the water is getting produced at source and it has to reach sink, and it should follow some other rules. So what actually happens is the source produces and the sink consumes, and all the other vortices in between, they neither produce nor consume. They just help the water to flow in the network. Okay. So the amount of water which goes into the source is 0, and the amount of water which goes out of the sink is 0, and for all the other vortices, the amount of flow that comes into the vortex is equal to the amount of flow that goes out of that vortex. Okay. So if you take a look at the previous graph, so what we are saying is the flow only goes out of the sink, and flow only comes into sink, and for all the other vortices, whatever comes in just goes out of it. Okay. So in a way, whatever comes out of the source is entirely reached at the sink. Okay. So that's what is we said here. So whatever flow that is go out of source is what is the flow that is into the sink. Okay. So let's look at the other example to make it more clear. So throughout this lecture, we will look at this graph as a standard example. So given this network, so what is the maximum flow? Okay. So can you try it and find what can be the maximum flow in this network? Okay. So let's look at the optimum solution. So the notation we are using here is, so for each edge we are writing flow by capacity. Okay. So for example, this edge has capacity 3, but the actual amount of flow is 2. Okay. So if you look at the previous terms we saw, so this is the capacity of an edge, and this is the flow that is actually in the solution, and from the source, what is the amount of flow that is going out? That is nothing but 2 plus 1. So 3 units of flow is going out of source. Similarly, 2 plus 1. 3 units of flow is coming into the sink. Okay. So if you look at all the other vortices, the amount of flow comes in. So let's look at B. The flow of unit 1 comes into B, and flow of unit 1 is going out of B. That is nothing but 1 plus 0. Similarly, for the vortex C, flow of 2 plus 0 is coming in, and flow of 2 is going out. Okay. So whatever the flow that starts from source has to reach sink entirely. So for the given example graph, that is satisfied, that property of flow in is equal to flow out for all the other vortices is satisfied, and also the main property that the flow of an edge should be less than or equal to the capacity of an edge is also satisfied. So we have a valid flow solution, and also we will see later that this is the maximum possible answer. Okay. So the maximum flow for this particular example of the graph is 3. So how can we actually find that maximum flow in the graph? Okay. So the algorithm is actually very simple. So you just keep sending some flow from source to sink. So let's say we have a path from source to sink. Consider the path S, B, C, T. So these are the capacities associated with the edges along the path. Okay. So if we send a flow equal to 1, so how does this path transform to? So following our flow by capacity notation, so we just increase the flow along each edge by 1. Okay. So if you look at this edge, so how much maximum flow, how much flow we can send? So at max we can send 3 more. Okay. So that is nothing but the capacity left. Okay. So instead of looking at flow by capacity, so if you look at the same path with capacities left, so it looks something like this. Okay. So after sending flow 1 along the path, the capacity left will be 3, 6 and 2. So how much more can we send along this path? We can send one more and it becomes 2, 5 and 1. And if we send one more, it becomes 1, 4 and 0. So what is the maximum flow we can send through this path? It is nothing but the minimum capacity of an edge. Okay. So in the given path, the edge CT has capacity 3 and it is the minimum along the path S to T. So the maximum amount of flow we can send is nothing but the minimum capacity of an edge present. So once we find such a path S to T, so all we need to do is find the edge with the minimum capacity, and all we need to do is subtract this minimum capacity from capacity of every other edge along the path, and we get this resultant path. Okay. So what we are actually doing is we are augmenting the flow along the path S to T. So the algorithm we follow is, we want to find a path from source to sink having an edge with minimum capacity left greater than 0. Okay. So that is called as, that we refer as the augmenting path. Okay. So augmenting path is nothing but a path from source to sink such that the capacity left on each edge along the path should be greater than 0. Okay. So if it is 0, then we cannot send any flow along that path. So if the capacity of each of the edge along the path from S to T is greater than 0, then it is called an augmenting path. Okay. So if there is an augmenting path, so what can we do? We can just send the flow, a positive flow along the path, and increase the overall max flow value. Okay. So the algorithm is very simple. So while there is an augmenting path P in the given network, increase the flow along P and adjust the capacities left. So as in the previous example, so we had a path from S to T and the minimum capacity was 3. So we just increase the flow to 3 and adjust the capacities left. Okay. So the final algorithm is also almost similar, but just we need to observe a little more to arrive at the final solution. Okay. So let's look at the same example again and let's see a step-by-step process of running MaxFlow. Okay. So initially the flow is 0 and this is the original network given. So let's find a path from source to sink. So consider this path colored in red. So the path S, B, C, T has a edge with minimum capacity 1. So we can send a positive flow along this augmenting path, and if we send a flow equal to 1, so the edge capacities left would be 0, 4 and 1. Okay. So now we have this network has flow equal to 1, and the weights on each of the edge is actually the amount of capacity left. So can we find one more path? Yes. So there is one more path shown in red from S to T such that the capacity left on each of the edges along the path is greater than 0. And again, what is the minimum such capacity? It is 1. So we can still increase the flow by 1. So now we got a flow equal to 2, and these are the capacities left on each of the edges. Okay. So now if you look at the current network we have, so can we find one more path from S to T traversing only the edges having capacity greater than 0? So we cannot go to S to B because it is 0, and if we go from S to A to C, and we can't take C to T because the capacity is 0. So there seems to be no path, no augmenting path from source to sink. Okay. So but the current value of the flow we have is just 2, but we have seen previously that the flow was actually 3. So in this particular instance of the MaxFlow solution, the flow is actually 3. Okay, so what are we actually missing? So let's look at that. So if you look closely, so there is a path from source to sink, but we cannot increase the flow, and there is already a flow 1 along this path, this red path. Okay, right? So look at the path with the green edges. Can we increase the flow along this path? If we try to send flow of 1 to S to A to C, it cannot go from C to T because the capacity left is 0. So why is it 0? Because there was already a flow along these red edges flowing along C to T. Okay. So but can we divert this red colored flow to some other path? Yes. So there is some other path, S, B, D, E, T. So if we can divert this flow to this flow, then we can actually increase the flow from S, A, C, T. Okay. So what we want is the green edges, when it tries to increase the flow, it reaches C and finds that we cannot increase the flow along CT. So what it does in turn is, so it tries to look at, so there is already a flow coming from S, B, C, T. Okay. So this flow coming from S, B, C, T, so can it find some other path and reaches sink, so that we can increase the, now we can increase the flow along S, A, C and T, that is the green edges. Okay. So all we need to do is we have to divert some of the already existing flow through some other path. Okay. So after diversion of some existing flow, we can increase the flow to 3. Okay. So after diversion, this is how the network looks like, and the maximum flow is 3, and that is the required answer. So what is this diversion actually? So this diversion doesn't look simple in terms of graph theory terms. So how can we simplify this, handling this diversion? So let's look at that. So for this we will introduce the concept of residual graph. Okay. So if you look at the edges with the capacity left, so if we send a flow F along this edge, so the capacity left from A to B is C minus F. So along with that, so what we do is we will add an edge from B to A, that is a reverse edge, and we will make the capacity of that edge is equal to F. Okay. So in a way, what does this represent is, so if you want to send a flow from A to B, the maximum you can send is nothing but the capacity left, that is C minus F. And at the same time, if you want to send some of the flow back, so the maximum flow you can send back is F. Okay. So that is nothing but the flow which is already there from A to B. So that will represent using a reverse edge and putting that F as the capacity. Okay. So if you were to send some flow back, the maximum you can send back is nothing but F. So after we got a flow equal to 2, so if you look at the residual network of this current graph, so it looks like this. Okay. So these are all the capacities left, and we just followed this notation. So whenever we send a flow F along A to B, we add a reverse edge from B to A, and the capacity for that is F. Okay. So let's make it more clear. So if you look at the original graph, there was an edge from S to A and it had a capacity 3. Okay, so if you actually send a flow 1 along that edge, so the capacity left now along from S to A is 2, and at the same time we will add a reverse edge from A to S with capacity 1. So that represents that if you were to send some flow back from A to S, so what is the maximum amount of flow you can send back? Okay. So now in this residual network, so can we find an augmenting path? Yes. So if you look at these red edges, so we are taking the edges with capacities left greater than 0, and we are able to reach sink starting from source. Okay. So A to A, S to A to C, C to B, B to D, D to E, and E to T, that is a sink. So and what is the maximum amount of flow we can send? That is nothing but the minimum capacity of an edge along that. So that is nothing but 1. So once we increase the flow by 1, so now the flow is 3, and this is the resulting network after augmenting. So now in this resulting augmented graph, so can we find one more augmenting path? So we cannot go reverse. So 1, 1, 0. So this is 0. So there is no more augmenting path in this residual network. So remember this. So we are not looking at the capacities left in the original graph. So whenever we look at, we are looking at residual network only. So if you recall, residual network is nothing but the original network with the extra reverse edges attached. Okay. So the final algorithm which works is, while there is an augmenting path in the residual network, increase the flow along the path and adjust the capacities left. Once we find that there are no more augmenting paths, we can actually stop the algorithm, and we are guaranteed that the solution is reached optimal, and that is the max flow we want. Okay. So you need to take care what is meant by adjusting in the case of residual networks. So when there is a flow F from U to V, so the capacity left along the edge UV decreases by F, and at the same time the capacity of the reverse edge from V to U increases by F. Okay. So this is the final algorithm. So as long as there is an augmenting path in the residual network from source to sink, increase the flow along that path and adjust the capacities left. Okay. So all the max flow algorithms follow the same method. So all we need to do is find some path from source to sink such that the capacity left is greater than 0. So that is nothing but an augmenting path. So find an augmenting path and increase the flow. So as long as we can find an augmenting path, so keep increasing the flow. So as you can see, the complexity of a max flow algorithm just depends on how do you find this augmenting path. So you are just starting from source, and you are traversing the graph by taking only the edges with capacity left greater than 0, and we are reaching sink. Okay. So that is nothing but a simple graph traversal, but you just consider the edges with capacities left greater than 0. So we can as well use a depth first search, or we can use a breadth first search to find a path, such a path from source to sink. Okay. So depending on the way you find the augmenting path, we have different types of algorithms. Okay. So if you use a simple DFS to find an augmenting path, the algorithm is by Ford-Fulkerson, and the algorithm is called the Ford-Fulkerson algorithm. So this is one of the earliest algorithm for the max flow problem. So in the worst case, it can happen that you increase the flow by 1 at each step. Okay. So find an augmenting path, increase the flow by 1, and again find the augmenting path and increase the flow by 1, so on. So to find an augmenting path, you may have to traverse the whole graph, that is all the edges once. Okay. So the complexity of a straightforward simple implementation of that algorithm will be number of times you do the DFS, that is nothing but the maximum flow, into the time taken for each DFS, that is nothing but the number of edges. So instead, if you find the augmenting path using a breadth first search, that is nothing but a shortest path. Okay. So if from source to sink, I want to find, so there is an augmenting path, but out of all augmenting paths present, I will pick the one which is shortest, that is in terms of the number of edges. So if you prefer the augmenting path with the minimum number of edges at this step, we have the next algorithm called the Edmond-Karp's algorithm, and it is shown that the complexity of this algorithm is O of V E square. Okay. So there is another algorithm with the following idea. So once to find a augmenting path from source to sink, so we traverse the graph and we gain a lot of information from that, and finally we find an augmenting path from source to sink. Okay. So to find the next augmenting path, so the previous algorithms were actually starting again fresh from source and finding an augmenting path. Instead of that, if we use the information we gained in the previous steps to find the next augmenting path, so that would actually decrease the complexity. Okay. So that's what Dinit's algorithm, blocking flow algorithm, does, and it is shown that the complexity for this algorithm is O of V square E. Okay. So all that our algorithm depends on is, so what is the next augmenting path we choose and how do you choose that? Okay. So let's look at a simple application of this MaxFlow problem. So without actually referring to the waters and the other networks. Okay. So remember that given a MaxFlow problem, it is not always some water or fluid that flows. Okay. So the main idea of the MaxFlow lies in how do you transform the problem into a MaxFlow problem. So let's look at a simple application. So you're in a city. So let's say you are in a country and you have some cities and we have some one-way roads connecting some pairs of cities. Okay. So the problem tells is, so you have a factory located at city X and it is manufacturing some products, and you have a distribution center at city Y and you want to send the goods from city X to city Y, and you can use the trucks to send the goods from city X to city Y. So the constraint is you are also given the maximum number of trucks that can drive along each road. Okay. So along each road we also give the maximum number of trucks that can go from along this edge. Okay. So now we can see that this looks like a MaxFlow problem. So you are given a network and the factory is the source and the distribution center is the sink, and the number of trucks you send along an edge should be less than or equal to the maximum limit that is given in the input, and the max flow along this network is nothing but the maximum number of trucks you can send from X to Y. So that's with the MaxFlow problem. So we did not go much detail into each of this algorithm, but we have given a overall idea of what each of these algorithm basically does. Okay. So let's look at now some standard variations and applications and some theorems related to MaxFlow. So the first natural question that comes is, so we look at that the example of the trucks we considered just now. So what if I have factory located at many different places in my country. Okay. So what we are looking for is something like this. So I have factory 1, factory 2 and factory 3, and I have my distribution center 1 and distribution center 2. Okay. So what is the maximum amount of goods I can transfer from all my factories to all my distribution centers? Okay. So that is what shown in the graph below. So we will do a simple transformation and still make it look like the standard MaxFlow problem which we have seen. So we will add a super sink in the graph, super sink and a super source. So this is the super sink we add, and this is the this is the super source we add, and this is the super sink we add. So and we connect the super sink to each of the source present, and we connect all the sink to the super sink T. Okay. So if we consider a flow in this transform network, so it is nothing but it has to start from one of the source and it has to reach the sink, one of the sinks present, and it has to finally reach the super sink. Okay. So after it add this super sink and super source, the problem is nothing but the standard MaxFlow problem where we have a single source and a single sink. So and one more observation is, if we also have a restriction on the number of goods that can be produced. So let's say in this example, so we also have a restriction on each factory. So each factory can produce only this many number of goods. So in that cases, we can actually add that constraint as a capacity along the edge from super source to that particular source. Okay. So let's say for the factory 2, at max 5 goods can be produced at factory 2. So we just take care of that by making the edge capacity from super source to that particular source as 5. Okay. So whatever that starts from source and goes along super source and goes along to this source cannot be more than 5. So that's how we capture those capacities of production, and we can also similarly have the capacity on how much maximum we can store in this distribution center. So let's say we also have a limit on the maximum number of goods that can be stored at this distribution center. So we can just add that particular limit on T1 by making the edge capacity from T1 to the super sink as CT1. Okay. So even if you have multiple sources and multiple sinks, and if you have a restriction on the number of goods that are produced and number of goods that are consumed at each of the factory and the distribution center, we can capture all these details by adding a super source and a super sink, and accordingly adjusting the capacities of the new edges we added. So still we solve the standard MaxFlow problem by transforming the given network. So the next variation we look at is, what if there is a capacity associated with a vertex? Okay. So what does this mean in an application? So if you look at the truck example, so from a city, so there are some trucks coming along the road from S to A, and they are entering the city A, and they are leaving the city A along an edge, let's say A to B. Okay. So previously we had a restriction only along the edges. So let's say maximum 3 trucks can be sent from S to A. So maximum 5 trucks can be sent along the road from A to B. So this was our previous problem. So now what if we have a capacity constraint on the vertex A also? Okay. So let's say, so what if the number of trucks that pass through A should not be more than 2? Okay. So along with the vertex, each vertex, we also have a capacity constraint which tells us, so what are the maximum number of trucks that can pass through the city A? But the problem we have solved, the standard MaxFlow problem, it just handles the capacities associated for only the edges. So the transformation we do here is, so split the vertex into two vertices V in and V out. So in this case, so it is A in and A out. So all the edges present which were going from S to A, so we'll add them now from S to A in, and all the edges which were from A to some other vertex, we will add from A out to this B. Okay. So and the capacity constraint which is imposed on A, so we'll add that as the edge capacity for the edge from A into A out. So now we can see that we have transformed this to a network where only the edges have capacity constraints, and still we captured the constraint put on a vertex by transforming it into an edge. Okay. So once you do the transformation by splitting each edge and adjusting the capacities on the edges of the resulting graph, still the problem is just a simple standard MaxFlow problem. So let's look at a standard application of the MaxFlow. So let's say we have a network given. So consider this network. So we have the vertices A, so A to B, B to C, and let's say we have A to D, D to E, and let's say E to T, and let's add one more vertex, S to F, and from F to E. Okay. So consider this network. So the question is, so what are the maximum number of edge disjoint paths from S to T? So what is meant by an edge disjoint path? So that is nothing but two paths from source to sink should not share the same edges. Okay. So in this graph, so if you look carefully, so we have this path from source to sink, and we have one more path from source to sink. So I'm just picking a random path. And are there any more paths from source to sink which does not go along the edge which is already considered? There is no more path. A path along S, D, E, T takes the edge ET again. Okay. So there are only two edge disjoint paths from source to sink in the given network. Okay. So this is nothing but, so if you have a capacity of 1 along each edge, then what we are looking for is just a max flow from source to sink. Okay. So how are we capturing this edge disjoint constraint? So once there is a flow from E to T, there is no more, we cannot increase the flow anymore because the edge capacity was only 1. Okay. So thus if you have all the edges with capacity 1, the max flow of the resulting network is nothing but the number of edge disjoint paths from source to sink. Okay. So similar to edge disjoint, so what if we have a vertex disjoint paths? So to differentiate between these two, so look at a simple example of S to A to B, A to C, B to C, C to D, D to E, and D connects to the sink. Okay. So consider this graph G dash. Okay. So how many edge disjoint paths are there? So there is a path S. So there is a path S, A, C, D, T, and there is one more path S, B, C, E, and T. Okay. And we are not using the same edge in both the paths. So these are two edge disjoint paths. So but what is meant by vertex disjoint path? So we cannot use the same vertex in more than one path. So in this graph G dash, so both these paths are going along the vertex C, so we cannot have two edge disjoint paths. Okay. So once we have a path S, A, C, D, and T, so we cannot now take the path S, B, C, E, T because the vertex C has been used already. So there is only one vertex disjoint path in this graph, and there are two edge disjoint paths in this graph. Okay. So again, so once we have a capacity restriction on a vertex, so all we do is we split the vertex into C in and C out, and we add the capacity of 1 from C into C out. So what this essentially does is, so once we increase the flow from along the vertex C, we cannot increase the flow anymore because the capacity is 1. So this actually captures the vertex disjoint path property we want. So one more concept related to max flow is the minimum cut. Okay. So what is a minimum cut? So given a weighted directed graph, so you are asked to remove some edges such that there is no path from source to sink. So consider this standard example again. So remove some of the edges such that there is no more path from source to sink. So one simple way is to just remove these two edges. So the sum of the weights of the edges we removed is 3 plus 1, that is 4. Okay. So what we are looking for is the minimum set of edges, the minimum sum of the minimum weighted set of edges to remove so that there is no path from source to sink. So is 3 plus 1 the minimum weight possible? No. So consider removing the edges SB and CT. Okay. So the sum of the edges we removed is 1 plus 2, that is 3, and as you can see there is no path from source to sink now. There is no directed path from source to sink, and the minimum cut is nothing but the set of edges SB and CT. Okay. So this is the minimum cut, and the value of the min cut is nothing but the sum of the edge capacities, that is 1 plus 2, that is equal to 3. Okay. And the max flow min cut theorem says that the maximum flow from source to sink is equal to the minimum cut to separate source from sink by removing some edges. Okay. So this is a very standard theorem, the MaxFlow min-cut theorem. And the next application is again a standard problem. This is called the maximum cardinality bipartite matching. Okay. So you are given a bipartite graph. So a graph is bipartite when we can partition the vertices into two sets L and R such that each edge present in the graph only goes across L and R. Okay. So there is no edge present between two vertices in L, and there is no edge present between two vertices in R. So such a partition of a graph is possible only if the graph is called, if it's a bipartite graph. Okay. So we want to find a matching in this bipartite graph. So matching is nothing but selecting independent edges. So in this particular example, a matching can be LR. So from A to U, and so let's label the vertices. Okay. So I am selecting the edge AU, CV and DX. Okay. So no two edges are incident on the same vertex. So if we had selected these two edges, then both of them are incident on the same common vertex. So we do not want to consider such cases. Okay. So we want to select some independent edges, and the problem is what are the maximum number of independent edges you can select. So that is nothing but the matching. So what is the maximum matching possible in this graph, in the bipartite graph? Okay. So again we will transform this problem to a MaxFlow problem. So add a source and add a sink, and connect from source to all the vertices on the left and from all the vertices on the right to sink. Okay. So we just assign a capacity of 1 for each of the edges in this transformed graph. Okay. So if you look at a flow along S to T, so let's consider a particular flow. So let's say the flow is going along this path. Okay. So what does this actually tell us is, so if we were to increase the flow again from some other path, you cannot increase along this direction anymore because the capacity was 1 and you have already used the capacity. Okay. So essentially once you pick an edge, so you cannot pick any edge along incident on these two endpoints anymore. Okay. So that is what we want in matching. Okay. So once we find a flow like this, so we are actually saturating these two endpoints such that further flow cannot pass through these vertices because the capacities are 1. Once we use this, so we cannot increase the flow anymore. Okay. So this essentially captures the independent edges property, and the max flow in the bipartite graph is nothing but the maximum cardinality bipartite matching we want. And there are some other related theorems to max flow, so we will not go in detail. So there is Koenig's theorem, which tells that the minimum number of vertices you need to select to cover all the edges is equal to the maximum matching, and this property is true only in case of a bipartite graph. And the Hall's theorem tells, so if you select any subset of vertices on the left side of a bipartite graph and look at the set of neighbors for this set selected, and if the number of neighbors is greater than the number of vertices selected for any set we select, then it has a perfect matching. So the perfect matching in the sense each of the vertices in the left side is matched to some vertex on the right side. And there is next theorem, the Dilworth's theorem. So if you are given a partially ordered set, the maximum number of elements in an anti-chain equals the minimum number of chains in any partition of the set of chains. Okay. So using this property, so we can actually find the minimum number of chains required to cover the set. That is nothing but the number of vertices present minus the maximum bipartite matching. Okay. So these are some advanced theorems which use the MaxFlow problem. So we don't actually need to go into deep details in these theorems if you are looking at just the basic standard MaxFlow problem. So that's it for now. So the references are the Corman CLRS textbook, and there is an excellent tutorial on Top Coder. So we have skipped most of the details of these three theorems. So if you want to go deep, so you can just look at the Wikipedia pages of these things. And there are some two standard applications of MaxFlow problem. So one is the baseball elimination problem and other is the cycle cover problem, which we will provide in the resources section of this lecture. Thank you.